Done.
Yeah. I'll stop the.
Yeah, Naru.
Oh. Okay. All right. So welcome to this harmonic analysis seminar today. Our speaker is our old friend Malabika Pramanik from University of British Columbia. She will speak on dimensionality and patterns with curvature. Yeah, Malabika.
Hello, everyone. It's a pleasure to thank Apurva for the opportunity to be here with you today. And thank you all for taking the time after the end of your work day and possibly after your dinner to actually join me for this meeting today. Okay, so what I'd like to talk about is the role that size or dimension plays in identifying patterns with curvature. So here's a plan for my talk. So there are two parts to it. The first is to explain what is an avoidance problem, give you some examples and do a maybe brief literature review, following up with the main results that I want to report on today. Okay, so what exactly is an avoidance problem? So we start with a collection of patterns, which is a collection of sets. And let me try writing this now, and you can tell me if this is visible. So hold on a moment, and while I pull this up again one more time.
There's some connectivity problem.
I think the issue is, yeah, hold on a moment. I think there is something with the writing of it that's not quite working. Hold on. Okay. Okay, are you able to, so I'm going to try the share again. Okay.
Yeah, we can see the screen now. Yeah.
You can see the screen now. Okay, now let me try writing and you can tell me if this, is this viewable so far?
Yes, underline.
Okay. All right. Okay, let's keep going again. So suppose we have script F, which is a collection of sets, and we are going to think of the members of F as the patterns that we are trying to identify. Okay. We will say that a set E avoids script F if E does not contain any member of script F at all. Okay. A typical avoidance question is the following. What is the largest size of a set E that avoids script F? In other words, let's say, of course, there is a lot of quantitative precision that's lacking in this question, but let's say this largest size is some number, say n, whatever that means. What that means is that if E prime is a set has size larger than n, then E prime must contain some member Okay. Now what is not clear right now is what exactly do I mean by size. So this word needs clarification. What is size? And where is all this happening? Where does E live?
May I ask you a small question?
Yes.
Just to have an idea. So for example, the Lebesgue number of some covering could be something like this, or it's nothing to do with this problem?
No, a size could be a size could be anything that measures the content of the set. So a Lebesgue covering number could be one possible way of measuring size. And in fact, in the next slide, I am going to give you certain examples of the notions of size that we will be working with.
One more naive question. Does the last line, which is handwritten, in this contrapositive way, it seems to remind me in some way, in some sense, of the pigeonhole principle. And if there are n+1 pigeons and n holes or something, but it's not quite that way. But
right.
Right.
So a pigeonhole, exactly. Well, a pigeonhole principle would probably be could be a sort of a very simple example, except in the case of the pigeonhole principle, there is no specific configuration that we are trying to identify. The pigeonhole principle just says that if there are, I don't know, n+1 many pigeons and let's say n many holes, at least one hole has to contain two pigeons. Right?
So can we somehow say something about two pigeons in one hole being the pattern, or multiple pigeons in one hole being
usually the patterns are more complicated than just the number of elements in a set. So that's okay. Maybe the good thing to say is what constitutes a pattern, and you will see in a moment why it's usually much more refined than saying counting the number of elements in a box. Okay. So I usually always mention this because chronologically, this is the first sort of pattern existence and avoidance question that I am aware of. So this is an example of an avoidance problem in the integers where the ambient space is Z. So it's an old result of Salem and Spencer and also Berendt that for sufficiently large capital N, there exists a subset E sub capital N large in this sense such that E sub n avoids all non-trivial progressions. So what it means is in the setting of the abstract question that I talked about before, what is the set of patterns here? The set of patterns script F is the class of all progressions. And the class, let me sort of, the class of k-term arithmetic progressions is a set of this form where A and D are integers and k is larger than or equal to 3. Okay. And this is an example of what I call a linear pattern. So this is an example of a linear pattern. And why linear? Well, that's because if you look at a progression and the progression is, let's say, x1, x2, xk, then you need k minus 2 linear equations to express this pattern. So xi plus 1 minus xi is equal to xi minus xi minus 1. So that's how this pattern is represented. Okay. Now, in contrast, here is another example. Originally due to Furstenberg and later modified or made more quantitative by Sarkozy. And this is again in the integers. This is what I'm going to call an example of a nonlinear pattern. Suppose that D of capital N is the largest possible cardinality of a set A. A is a subset of the first n natural numbers, and it avoids all pairs x, x plus z square. So the set of patterns here is of the following form. This pattern consists of pairs x and x plus z square. X and z are positive integers. And this property of capital A, this property that it avoids all such pairs is actually equivalent to saying that the different set A minus A does not contain any perfect squares. Okay. And it's a result of Furstenberg and Sarkozy says that if capital A is such a set, then the maximal such cardinality of A divided by capital N has to go to 0. In other words, every set A of positive density What do I mean by positive density? This is where the limit as n goes to infinity of the cardinality of A is positive. So every such set A contains pairs x comma y with x minus y being some z square, non-zero. Okay, all right. Now this is an example of a nonlinear pattern. And this distinction will be important for us. Now it's very natural to seek comparisons between the discrete setting and the continuum setting, with the cardinality in the integers being replaced by notions like measure, density, or dimension in R. And sometimes the measure could be the Lebesgue measure, the density could be, let's say, the Banach density or the asymptotic density, and dimension. There are so many possibilities here, the Hausdorff dimension, the Fourier dimension, and so on, and others. Okay. However, it's not true that every pattern question in the integers, if extended verbatim to the continuum setting, makes sense. So maybe we could start by just looking at the two examples. Let's look at example 1, but recast on the real line. And it says that does we could say, does every large set in R contain arithmetic progressions? And this is a perfectly meaningful and in fact very well studied question. Whereas if you look at example 2 in R, where we say, does every large set in R contain pairs of the form x plus z square? This is not really a sensible question at all, because if you take any large set E, and in fact, it doesn't even have to be large, if it's just a 2-point set, and x is less than y, or sorry, x is greater than y, then this is of course trivially true. So this makes no sense. However, one can maybe change one's point of view a little bit and cast this problem in R2. So let's try, this is going to be our guiding example. So this is example 2 in the setting of R2. And we want to ask the following question. Does every large, and large is to be suitably interpreted, does every large subset of the plane contain a set of the form x comma x plus z square for some non-zero z? And we are going to concern ourselves with this question for today. Okay. So before I move on, let's see if there are any questions so far.
Counting primes would be a avoidance problem as well, right?
Counting primes?
I'm avoiding composites, like in discrete setting.
Well, one could cast it as an existence problem or an avoidance problem in the following way. One could say that what is the largest length or block of integers one can go to without encountering a prime, and that could be, it could be cast as an avoidance problem. Or one could take, let's say, integers that are expressed in terms of certain digits and ask how large of a set can one construct which let's say avoid primes. Yes, so it depends on how you formulate the question. So such questions can certainly be deemed avoidance or existence problems. Yes.
And maybe in these kind of settings, maybe lattice points or some kind of a quasi kind of a crystal, where meaning large sets which avoid some kind of a crystal structure. Is that probably an interesting question?
That's possible. I don't know. I would have to sort of see the more concrete version of it. But whether it depends, I think, on how you formulate it, and not, I mean, of course, given my expertise, most of the pattern questions that I talk about, they have either an analytic or a geometric flavor to it. But there are many pattern questions out there which are driven by more different types of applications. So it's quite possible that what you are talking about would fall in that framework.
Okay, thank you.
Okay, So let's say I think many of you are already familiar with the notion of Hausdorff dimension, but for completeness, I'm just going to do a very quick review. All sets in this talk are going to be Borel. Let's say that capital A is a Borel subset of the n-dimensional Euclidean space, and S is a number between 0 and n, not necessarily an integer. The S-dimensional Hausdorff measure of A is defined in the following way. So take A and consider the coverings of a countable covering of A using balls whose radii are less than a fixed quantity delta. For every such cover, compute the summation Ri to the power of S. Remember, S is the exponent. And then take the infimum of these sums over all countable covers of A for this fixed delta, and then take the limit as delta goes to 0. This is the S-dimensional Hausdorff measure of A. It is a property of the Hausdorff measure that for any set, there is a threshold S0 below which the S-dimensional Hausdorff measure of A is infinite, and above which the S-dimensional Hausdorff measure is 0. And that threshold S0 is called the Hausdorff dimension of A. Okay. There is an alternative, an equivalent description of the Hausdorff dimension, goes by the name of Rossmann's lemma, that says that the Hausdorff dimension can equivalently be expressed as the supremum value of alpha between 0 and n, for which there exists a probability measure mu supported on the set A satisfying a ball condition. So what the ball condition says that the measure that mu assigns to any ball of radius r is bounded above by a constant multiple of r to the power of alpha. So we are going to call such measures a Frostman measure of order alpha. Okay. Now, the dimension is a notion of size, and it's a really good sanity check that it actually conforms to all our usual traditional notions. So the Hausdorff dimension of a line is still 1. The Hausdorff dimension of a plane is 2. But this notion allows us to actually assign a notion of size to much more rough objects where the differential geometric structure of lines and planes fails. So for example, if you look at the Hausdorff dimension of the Cantor middle third set, that's log 2 over log 3. Okay. And similarly, there are lots of very interesting fractals. I've just included 2 examples here, the Sierpinski triangle, whose dimension is log 3 to the base 2, and maybe the Brownian graphs of Brownian motions. Again, its Hausdorff dimension is 3/2. Okay. So here is a quick, it's a very, very short and incomplete list of some of the recent work in sets with and without polynomial patterns. There is no way I can do just this area is really buzzing with activity, some in the setting of integers and finite fields, others in the continuum setting. Maybe what I can do is as I go through the talk, I will refer back to some of the work cited here and point out the connections. Okay, so this brings me to the main results of this talk. in 2021, Kuca, Orponen and Sahlsten proved the following theorem, the continuum version of a Sarkozy type theorem. So what they prove is the following. There exists an absolute constant epsilon positive such that for every compact K whose Hausdorff dimension is larger than 2 minus epsilon, there exists a point X in K and a non-zero real number Z such that X plus ZZ squared belongs to K. So this pattern, the nonlinearity of this pattern is essential. So I'm going to make that note here. Nonlinearity is essential. Okay. And why is that? That's because one knows that there exist graphs gamma, and by a graph I mean a set of the following form x comma f of x, x in 0, 1, and subset of the unit square with Hausdorff dimension 2. What does this have to do with anything? The existence of such graphs means that gamma cannot contain points of the following form, let's say x1, x2. So this is my x, and x1, x2 plus z. Why? Because you see, gamma is a graph, and being a graph, for every x1, its x2 coordinate is uniquely determined by f of x1. So there cannot be two distinct x2 coordinates for the same x1. And the fact that this graph is space filling, it has full dimension 2, that means that there is no analog if this is replaced by, so no, not true, for the linear pattern 0, z. Okay. So this was very exciting for a number of reasons. So this result relies, so this relies only on the Hausdorff dimension of K and on nothing else. And this was a substantial improvement on prior work. So the prior work was of two types. So either the prior work used the fact that K had positive Lebesgue measure, or K has Lebesgue measure 0, so K has fractional dimension. But we had to put additional restrictions, but had to support measures which have Fourier decay. So Kuca, Orponen and Sahlsten actually strengthened, so their work was progress on both fronts. Okay. So motivated by their work, we wanted to sort of see how far we could carry. So to what extent their result was representative of the state of matters. So let's sort of take a moment to understand these definitions. So suppose
Malavika,
that
just
yes.
so in the last theorem, the z is a real number.
Yes, that's correct. So Z is in R.
Okay.
So Z is in
because
R.
because the first examples were in integers, so here you can avoid. I mean, if it's large enough, the dimension, you say that k minus k has some point of this graph of.
So this
Z.
is the result that I'm trying to. So remember, this
Yeah.
is I posed this question: does every large subset of E in R2 contain a set of the form x x plus zz squared? So this x is in R2. Z is in R.
Yeah. Okay. Thanks. Yeah.
Okay, and therefore, and the fact that there can be graphs of full dimension means that you cannot have x plus 0 comma z, but Kuca, Orponen and Sahlsten's claim was you can have x plus z square.
Yeah, thank you.
Okay, great. All right, so let's continue on with the definitions. So suppose that phi is a smooth function in one variable, univariate but vector valued, and suppose that t naught is a real number. We are going to say that phi is in the polynomial class if every entry of phi j, is a polynomial. All right. Second, we are going to say that phi is a finite type at a point t naught if there exists a positive integer capital N such that given any direction in d-dimensional Euclidean space, one can find a little n between 1 and capital N such that the nth order derivative of phi at t naught when projected in the direction of u is non-zero. So I'm going to maybe give you some examples. So if you are looking at phi in the polynomial class, you can have phi of t equals, let's say, t comma t, or t comma t square, or t square t cube plus t to the 4. So these are all examples of functions in the polynomial class. Among these, t square and t square, these are of finite type. This one is not. Okay. And finally, we'll say that phi vanishes to finite order at t naught if phi at t naught is 0 and phi is of finite type at t naught. Okay.
So you don't want its little n to be equal to 0. You want from 1 to capital N.
Oh, absolutely. So this derivative, that these are actual derivatives, is very important.
Right. And so basically, roughly speaking, does this sort of say that they should not be spanned in any hyperplane so that something is perpendicular to it?
That is exactly well, yes, for polynomials, that's exactly it. So here is an example of a smooth function. So let's say you have x comma e to the power of minus 1 over x square. So suppose this is my phi of x, okay, or phi of t. So t comma e to the power minus 1 over t square. This is my phi of t, this is smooth, and this vanishes at t equal to 0, but not of finite type. And it is not, so it's not in the polynomial class. And it's not of finite type.
Sorry, and you're defining it to be 0 at 0, you mean?
And it vanishes. So it vanishes at t not equal to 0. So phi of 0 is 0.
Right. Okay.
And what you said about being lying in a lower dimensional hyperplane, that is definitely true for functions phi in the polynomial class. If you have a set of polynomials and they are not of finite type, then this set of polynomials has to be linearly dependent, which means then they lie on a lower dimensional hyperplane. Right. Okay.
And again, of course, you don't ask for any upper bound on the degrees of these polynomials in the first definition, or
no upper bound on no assumptions, but our results will of course be uniform given these upper bounds, but no assumptions so far.
Okay, thanks.
Okay, all right. So here's the main result joint with Benjamin Bruce. So the first result says that suppose you have phi in vector valued in dimension D, which vanishes to finite order at some point. And suppose that Z is the zero set of phi. Then we find an absolute constant epsilon such that every compact set K in dimension D whose Hausdorff dimension exceeds D minus epsilon must contain a two-point configuration of the form x comma x plus phi of t, where phi of t is non-zero. So this is an extension of Kuca, Orponen, and Sahlsten's work from the ZZ square setting to all patterns that are smooth of finite type. So that's the first result.
Sorry, that's if I may. If in your previous examples you gave one of them was t comma t square.
Yes.
Which is the z square thing you're saying here.
That's right.
Right. And if sorry.
Yeah, go ahead.
The different question, if you were going to say add something more to your answer here.
So I'm saying that one extension is that instead of t comma t square, this extends to all polynomials, and in fact all smooth functions as long as they are of finite type.
Right.
Okay.
Yeah. And my other question was sort of is this epsilon even in their paper or in yours? How constructive is this epsilon?
Yeah, that's a great question. So their work. So let's go back to Kuca, Orponen, and Sahlsten. So their result is constructive in the sense that a careful tracking of their methods is going to produce a particular value of epsilon. So the proof is not non-constructive. However, I think that maybe it's a good place to state a conjecture. They conjectured this themselves. So what they say, so their conjecture is that this epsilon should be 1/2. But their result gives an epsilon that, so the epsilon from their proof is much smaller.
Okay. So if you're writing something, I'll just say I could not see it.
You couldn't see my writing?
No, not right now. Naru, can you see it?
Yeah, I can. There is a lag. So.
Okay. Maybe it will appear.
So I said conjecture epsilon equals 1/2, and I wrote that epsilon from the proof is much less than 1/2.
Yeah, I can see it now. And the reason I was asking was because now I'm going to go to your result.
Yes.
If how constructive or something is your epsilon in the sense of I'm reminded of this kind of Grothendieck inequality kind of thing.
Yes.
How dependent on D is the epsilon? Can you say that across all D and across all phi from R to RD, the same absolute constant epsilon works? Or that's
right. So yes, we can actually say a few things in that respect. So let me say what are some of the things. So our epsilon that we can get. So the proof is constructive. So we get actual concrete values of epsilon. But currently we have no reason to assume that these are optimal. But the important thing, though, in regard to this other part of your question, this epsilon that we get is uniform for phi in the polynomial class of degree d, a finite type. And with bounded coefficients.
Great. And the epsilon depends on d, it grows with d?
It grows with d, correct.
Okay.
So as long as this d is fixed and the coefficients are bounded, we have this epsilon only depends on the 2 and not on the specific polynomials within this subclass.
Great, thanks.
Okay. All right. All right, so we actually have within the polynomial class, we have a converse. So the converse says that suppose that phi is in the polynomial class and does not vanish to finite order at any point, then for every epsilon positive, we can construct a compact subset of Rd, K, whose Hausdorff dimension exceeds d minus epsilon and which avoids all patterns of the form x plus phi t for x in Rd and t not lying outside the zero set of phi. So this is the exact converse with the additional assumption that phi has to be in the polynomial class. Okay. So for polynomial patterns, then, we have a characterization that high Hausdorff dimension is equivalent to the existence of all kinds of finite type polynomial patterns. Okay. All right. So maybe I have 10-15 more minutes. So I'll spend that time discussing the proof. Are there any questions so far?
Yeah, just one question. So how important is the compactness of K?
Oh, it's not important at all, because if you start with a K that is non-compact, you can always restrict it to a compact subset where it will maintain the same dimension, and you can run this argument there. So it's without loss of generality. You can assume compact.
Oh, okay. Thank you.
Okay. So let's go over some of the main ideas in the proof, and for this I am going to, for the ease of exposition, I'm going to stick to the work of Kuca, Orponen and Sahlsten, where the ambient dimension is 2 and the pattern to be avoided, the phi, is z squared, because that's, I think, the simplest for me to explain. Now, the first step, and this step is a common feature whenever we are trying to locate configurations, is to identify an integral that helps you locate a configuration. So I want to tell you what this means. So what is an integral that locates configurations? So in this case, so let's say what do we have? Let's remind ourselves that we have K subset of R2. We have a measure mu. So mu is a Frostman measure. Supported on K. And what we are trying to get to, so what we want is to show that x plus z square is contained in K. So we are going to prove this by looking at a certain integral, and the integral here is the integral of mu convolved with pi x d mu x. And I'll explain what these are. What is pi? Pi here is the Lebesgue measure on the parabola t squared. Okay. All right. So the goal is to show that this configuration integral I is positive. And I'll explain why this does the job.
You mean the Hausdorff measure on the graph? Oh, I didn't understand.
Sorry, could you say that again?
The pi here is the
The pi is a
Hausdorff.
measure. So it's a measure. So let me draw a picture here. So this is the graph. This is the parabola t square. Okay. And so let's say pi is between, let's say, -1 and 1. And how does it work? So remember, a measure is uniquely defined by its action on functions, right? So suppose you have a test function phi and you have mu acting on it. What does it do? All it does is that it takes phi and it evaluates it on the parabola t squared and it integrates it, let's say, from -1 to 1. So that's, sorry, this is, I'm sorry, don't mean mu, I mean pi. So this is the Lebesgue measure on the parabola. So it takes a two-dimensional function, a bivariate function. It restricts that function only to the parabola and average integrates along it.
Okay. Thank you.
All right.
So I guess you will convolve with approximate identities to get functions, right?
That's correct. So if
like
the way to do it is you can, usually the traditional method is to say that I'm going to identify this.
Limit and
yeah, like
that
this.
it's positive.
Yes,
yeah,
that's right. So why is it enough to show the positivity of this? So let's take a look. Suppose this were positive, what that would signal, so what that would imply is that the integrand must be positive. So that means there has to be an x which on one hand is contained in the support of mu, so that this part is positive. And on the other hand, it's also contained in the support of mu convolved with pi. And remember, what is the support of mu? The support of mu was k. And what is the support of mu convolved with pi? So it's k minus t squared. So that exactly means that there has to be x has to be in k and x plus t squared also has to be in k, which is what we wanted. Okay, so our goal is to prove the positivity of the configuration integral. All right. Now, going back to the proof overview, the next step, and this is one of the really novel contributions of the work of Kuca, Orponen, and Sahlsten, is to identify this property called a spectral gap. Now, in past work, proving positivity of the configuration integral always relied in some form on Fourier decay of the measure. Now, what Kuca, Orponen, and Sahlsten do, they show that if a probability measure obeys a spectral gap property, then it automatically contains patterns of the type ZZ square. So let me try to explain why that's the case. All right. Okay. So so let's recall that we have this dimension of the Hausdorff dimension of K is less than 2. Okay. And as a consequence of it, I know that no matter what measure you put on it, the L2 norm of that measure has to be infinite, because if it was not infinite by Plancherel's theorem, it would be an L2 density and its support would be of positive Lebesgue measure. So we know that the L2 norm of mu hat is a divergent integral. We are going to say that, however, even though we are dealing with a divergent integral, we can place some restrictions on how this integral diverges. So we are going to say that mu obeys a spectral gap condition with parameters a and b and these a and b are typically larger, much bigger than 1, if the following holds, namely, if you look at the L2 norms, the mu hat xi square, but only on the annulus, a between with mod xi between a and b, then within that annulus, it actually is really small compared to a. So of course, one cannot expect to have something like this for all A and B. If such things were true, you might actually end up proving that mu is in L2. That won't do at all. But for fixed constants A and B, this is something that's at least okay to ask for. And the proof relies on the fact that knowing this for certain pairs A and B suffices for proving positivity of the configuration integral. So let me explain how that proof goes. So there is this I, the configuration integral, and I'll remind you what this is. This is mu convolved with pi d mu. And I'm going to write this in 3 separate parts. The first part, and so let me remind you what mu delta is. So Naru asked me about this. This is the delta thickening of a mu. In other words, convolving mu with an approximate identity phi delta. So phi delta of x is delta to the power of -2 phi of x over delta. So I'm going to write this as mu sub A inverse convolved with pi d mu plus the integral over mu B inverse minus A inverse convolved with pi d mu, and the tail mu minus mu sub B inverse convolved with pi d mu. Okay, so these are the 3 pieces. Now the first piece is the dominant term. So this is the dominant term, and using the absolute continuous nature of mu sub A inverse, one shows that this is larger than a to the power of -1. The last part, this part over here, This is the tail of the integral, and it's fairly standard to recast this integral in terms of the Fourier transform. And in terms of the Fourier transform, the integral can be written as mod xi larger than b, mu hat of xi square, pi hat of xi d xi. And this is where the curvature plays a role. Because we are on the parabola, the pi hat has some decay, and it actually decays like mod xi to the power of -1/2. And this means that you can pull out a power of b, and what is left is the energy integral of mu. So if b is very large, this is much smaller than A inverse. So this is much smaller than A inverse if b is very large. Okay. Neither of these two arguments actually help with the middle situation, and it's precisely here that the spectral gap condition is needed. So this is where this feeds in. So this integral here, again, using the Fourier formula, is exactly of the same size as mod xi less than b of mu hat of xi square pi hat xi, and pi hat of xi, this is of course always big O of 1, and this condition here tells you that if you have a spectral gap property, this part is not terribly large, and in fact smaller than the main term. So it's in the middle range that the spectral gap condition comes in handy. Okay, so the one last thing for which I'm not going to have a whole lot of time is how Kuca, Orponen, and Sahlsten end up showing that the spectral gap condition can actually be achieved for measure. So in fact, any set of large Hausdorff dimension will support a Frostman measure with the spectral gap property. So that is something that's another important feature of their work. So what I'm going to do instead is I'm going to maybe just give you a very general idea of their proof. So if phi is in the Schwarz class, then notice that the spectral gap property is a triviality because you can always make sure that this holds true. Okay, so what they do is they take these parabolic rectangles, and these parabolic rectangles are rectangles of the form which are roughly 2 to the minus j on one side and 4 to the minus j on the other side, and they look, and Kuca, Orponen, and Sahlsten find a way of looking at children of these . Okay, so a child this is the first generation children. So let's say if the large one is R, and if these smaller ones, these children are Q. So what they try to do is they try to decompose these parabolic rectangles into, so this is an example of a parabolic rectangle. And they construct a measure mu by piecing together measures supported on Q, and these Q are, let's say, some large generation children, generation T, children of R. And this mu sub Q is carefully crafted in such a way that mu Q hat is close to phi hat. because phi hat is the one which seems to have the desired property. So these mu q's are actually Frostman measures supported on Q, and they are weighted in such a way so that their Fourier transform is close to phi hat. Okay, so I'm being deliberately vague because there are a lot of details to be filled in here, but I think I'm already out of time. So what I'll do is I'll stop here and wait for your questions.
Yeah, thank you. Any questions? Okay, maybe I will ask. So in your result, you follow the same methods?
Well, yes and no. Let's see. To a certain extent. For example, we also rely on this step, this creating measures with spectral gap. We definitely need that result or at least we need to use that idea and extend it to our setting. Something that doesn't automatically extend to our setting is this notion of parabolic Hausdorff dimension. So Kuca, Orponen and Sahlsten brought this into play because they were looking at the pattern ZZ square, and they had to craft their notion of dimension in a very special way so that it fit the kind of patterns they were trying to identify. So we had to do some work because we are dealing with general finite type patterns. We had to sort of come up with a variant that would sort of be a working substitute for this parabolic Hausdorff dimension.
Okay.
And something that was not present in their work at all is new is this converse, because Kuca, Orponen and Sahlsten's work was really about showing proving the positive direction. So the converse side, what we need to do is in any dimension, we have to also show that there are very large sets that do not contain any polynomial patterns if those polynomial patterns fail to be of finite type. And that's a very separate construction of a space filling graph that was not present at all in Kuca, Orponen and Sahlsten's work, which we had to do.
Okay, just one more question, peripheral in some sense. So this bringing in the spectral gap, as you said, seems to be a new tool in some sense.
Right.
Some of your early results with Isabella Laba used the Fourier dimension, right? So
yes,
can one use this in those results to get rid of the Fourier conditions on Fourier dimensions?
Meaning can one use the spectral gap condition to get rid of the assumption on Fourier dimension? Yes. So you see this, where did I say this? Hang on. Here. So remember here I talked about prior work where either K had positive Lebesgue measure, and this was like the work of Bourgain on the nonlinear Roth theorem, and let's say other people like Guo, Durchik, and Roos. But in the other direction, this is the one direction that Naru, you were talking about, is the sets have fractional dimension, but we had to assume that it had it supports measures with Fourier decay. This is the work that was jointly with Isabella Laba, our students Vincent Chan, our postdoc Kevin Oreo, and others. Robert Fraser and so on. So we have a body of work that supports the statement that if a set has both large Hausdorff dimension and Fourier dimension, and that's precisely this condition, then we can prove existence of many kinds of patterns. But one of the roadblocks in this field has been the removal of the Fourier decay condition and resting just on Hausdorff dimensionality. So the work of Kuca, Orponen, and Sahlsten can be viewed as maybe the first progress in getting rid of that roadblock, because they assume Hausdorff dimensionality alone and use the spectral gap as a substitute for the Fourier decay assumption. And then they prove that Hausdorff dimensionality alone will guarantee measures with spectral gap.
Yeah. Okay.
So in that sense, it is a strengthening of our past result with Isabella Laba and others.
Yeah, all right. Thank you. I think Rajesh.
Yeah, I have also like curiosity kind of question. So there should be some motivation for studying these problems. Could you say something about why? Meaning, because it seems to be like, as you said, I mean, it has generated a lot of interest. So, I mean, I wanted to understand what are the motivations for this? Yeah.
Yeah, so I think their motivations, there are many, motivations come from many different directions. So let me just look at some of the people who have worked in this area. So the work of Bergelson and Liebman, this work and the original work of Furstenberg, their motivation came from ergodic theory, and their tools are also ergodic theoretic. So these are results about how measure preserving transformations behave, limiting measures. So this is that's one direction. Now the work of Bourgain, Chang, so these results are on one hand motivated by number theory, because somebody actually already pointed out questions regarding primes and so on. So the motivation comes from number theory on one hand and additive combinatorics on the other hand. So this is to do with structures of sets of in numbers and finite fields. Okay. Now, in the continuum setting, what is the motivation for studying these questions? And once again, the motivation comes from many different directions. Some of this later work, these have connections with multilinear integrals, and these are of an operator theoretic flavor. And the work of, let's say, Keleti, Maga, Mathe, and so on, these have and also the work of Falconer, Yavicoli, these are actually related to the study of fractals. So fractal geometry and geometric measure theory. So maybe a short answer to your question is that there is no one motivation for studying these type of problems. They occur in the investigation of different types of questions, although at heart, they are really a question about identifying patterns or avoiding patterns. So maybe the reason this area has caught on is because it sort of interfaces with so many different other areas, and many different tools can be brought to bear on the study of these problems.
Yeah, thank you very much.
Any other questions, comments? So if not, let us thank Malabika for a very wonderful talk.
Thank you. Have I stopped presenting?